Healthcare AI has a problem that is easy to miss. A model can look strong when it is developed and behave very differently when it meets another environment. This is one example. The Epic sepsis model had already been implemented across hundreds of US hospitals, but an independent JMA validation reported an AUC of just 0.63 along with poor calibration. But the second result is even closer to the problem we wanted to investigate. Researchers studying hospital mortality models found that discrimination could remain stable while calibration deteriorated over time. In simple words, the model may still rank patients reasonably well even when the probabilities themselves become less reliable. And this is why monitoring the information environment matters. The FDA notes that clinical data systems, protocols, and patient populations change across time and sites, and those changes can alter model behavior. So we asked, can we deliberately crash test this kind of hidden reliability failure before deployment? This is Cliniverse, the healthcare AI reliability lab, and the entire project can be summarized in one sentence. The ranking still looked reasonable, the probabilities did not. In our final holdout, AUROC moved only from roughly 0.835 to 0.824, but mean predicted risk fell from around 14% to 10.4%, while observed mortality was 14.625%. That gap is exactly what Cliniverse is built to expose. And this wasn't one cherry picked experiment. The process involved 141 candidate patterns, 20 development resplits, and 4,000 patient holdout confirmation. So, why can this happen? AUROC mainly asks a ranking question. Imagine patient A died and patient B survived. If A receives the highest score, the ordering is correct. Now both scores can shift downwards, but as long as A still ranks above B, that ordering survives. So the ranking metric may still look good, but if those scores are being interpreted as risk probabilities, there is another question. Do the numbers still mean what we think they mean? Cliniverse separates the ranking question from the probability reliability question. Think of the healthcare model as a car. Cliniverse is not another car. Cliniverse is the crash test facility around it. We take a frozen healthcare model, deliberately stress its information environment, measure what changes, compare that change against controls, and turn the result into reliability evidence. So, this is designed for ML researchers, model developers, and model governance teams, not as a diagnostic application for doctors or patients. This is the complete Cineverse workflow: stress, control, search, stabilize, freeze, confirm, evidence. First, we deliberately withhold candidate information patterns. But simply deleting data is not evidence because removing information usually hurts a model anyway. So every candidate gets its own amount matched control. Then we search on development data, test stability across repeated resplits, freeze the model and statistical contract, and only then execute the final patient level confirmation. Underneath that workflow is a frozen ML pipeline. We start with the PhysioNet Computing in Cardiology 2012 dataset, which uses a 24-hour observation cutoff and evaluate a frozen XGBoost mortality model with flat calibration. The reliability engine performs the stress and matched control experiments on 8,000 development patients. After stability selection, the model, pre-processing, selected pattern, and statistical contract are frozen. Then comes one 4,000 patient set C confirmation. Finally, the committed evidence feeds our React application. The website is therefore an evidence interface and not a live clinical inference system. This is probably the most important experimental decision in Cliniverse. On one side, we remove the candidate information pattern. On the other side, we randomly remove the same number of cells from the same patients. So the question becomes, did this particular information pattern hurt more than deletion burden alone? We evaluated 141 candidates across 20 development resplits. The exact BUN plus glucose plus sodium pattern appeared in 11 out of 20 top level resplits. And that matters because 11 was exactly the minimum majority threshold. We show that honestly rather than pretending the stability was overwhelming. Then we froze the candidate and evaluation contract and executed the patient level confirmation points. On 4,000 patients, BUN plus glucose plus sodium produced an excess probability loss of plus 0.018347. Its one-sided 95% lower bound was plus 0.12421, remaining above zero. At the same time, AUROC moved from 0.834994 to 0.823534. So that's a drop of only 0.011461 below our frozen zero point zero 0.02 ceiling. Yet, mean predicted risk fell from approximately 14% to 10.4% against observed mortality of 14.625%. Probability behavior degraded while ranking changed only modestly. This is the failure Cliniverse was designed to find. But we didn't want this result trapped in a notebook or static chart. So let me show you Cliniverse itself. This is the live Cliniverse workspace. Here is the one frozen pattern that reached holdout confirmation: BUN, glucose, and sodium. And here are three headline signals: excess probability loss, its positive lower bound, and the comparatively small AUROC drop. The investigation timeline below shows how that result was discovered, frozen, and confirmed. This is the stress lab, and this distinction is important. This is replay, not a new holdout experiment. The patient level confirmation was pre specified and frozen before patient level evaluation. It has been consumed and set C is now spent. I can replay a lower committed severity or a stronger one and watch how the saved experiment responds. These controls read committed artifacts. They do not retune the model or reopen the final holdout. Next is the reliability report. This is where the thesis becomes visual. Look first at the ROC curves. They remain very close. Now look beside them. Probability loss increases. The mean predicted risk shifts downward, and the calibration and risk distribution views change much more clearly. So a judge looking only at discrimination could walk away with very different impression from somebody examining the model's probability behavior. Next is the artifacts. So we also wanted every important visual to be inspectable. The artifacts page connects the interface back to the committed prediction evidence and derived views. So this is not a dashboard where we manually typed impressive numbers. Provenance is part of the product. And finally, we preserve the results that failed in the experiments section. M5V1 did not clear its own primary criteria. We kept it. The latest stability aware search passed its gates. The final set C confirmation was executed once, and that holdout is now spent. For us, negative evidence is part of reliability engineering too. So, Cliniverse does three things: discover fragile information dependencies, verify a frozen claim under a fixed evaluation contract, and inspect the evidence and provenance afterwards. The boundary matters too. This is a research and model governance prototype. It is not clinically validated and it performs no patient level decision making. The goal is simpler: find reliability, weakness before high stakes deployment rather than after. Healthcare AI should not earn our trust simply because one headline matrix looks good. Clinic work asks one harder question: when the information environment is stressed, does the probability still deserve the trust? Before we trust the prediction, we should crash test the probability. Stress, control, freeze, confirm. That is Cliniverse, the healthcare AI reliability lab. Thank you.